Okay, so we are seeing that Cartesian is not the only way where we can calculate the volume or we can move ahead as far as dimensionability is concerned. So there are other ways also in which I can have integration. So triple integration and calculation of the volume and even more. So that's what we saw that others are also possible, like polar wave or cylindrical wave or spherical. So the new things what we are seeing now, typically what people do is kind of single variable integration or calculus, and then they have typically Cartesian. But new thing what we saw, when we want to grow in dimensionability, then beyond 3D we grow in the density function. This is what we have seen. In the density function we can grow. Okay, not only in density function on the Cartesian coordinate system that we can grow, we can grow in a way that kind of in polar fashion also. So polar can have polar cylindrical or spherical. They also can have a density function. But the orthogonality, what we see through the Cartesian, is different in the way it is. Like in Cartesian, we have x-axis and we have y-axis and we have z-axis, x-axis, y-axis, and z-axis. This is what we consider orthogonal. Okay, whereas the orthogonality is not restricted to the Cartesian only. Orthogonality is orthogonality grows in polar side also. Like if I have a circle, if I have a circle, in this circle there is a radius. If this is the radius, then this is one dimension, and there is angle, that is another dimension. So circle can grow in the circumference if radius grows. Okay, and circle forms circumference when radius rotates. So rotation angle and radius, so they both constitute orthogonally. They constitute orthogonally to form the circle. So polar coordinate system. Polar coordinate system. If I have a circle, cylinder. Okay, if I have a circle and then cylinder. So if r and theta are independent component in a 2D plane, then if dependent component is orthogonal to both of them and it is along vertical, then it is cylindrical coordinate. Now we so whatever we saw now, that angle and radius, they are in a surface, that is xy plane. But what about if I have a sphere? Okay, if I have a sphere, then the radius in the sphere is 3D. If I have polar coordinate in a surface, if I have xy plane, I have xy plane. In the xy plane, I have the radius and I have the angle. But they are in xy plane and they are independent component. Dependent component is z, that constitutes cylinder. Now, if I have a sphere, so sphere again has radius, but it is not confined to a surface. Okay, so this radius would kind of move in any direction. So typically if I say xz plane, then radius would move like this. If I say xyz plane, then radius would move like this. Anyway, there is no xyz here, but this is how it is. So independent component is radius that is not confined to a surface. So radius, if from vertical, if this is vertical and this is radius, then angle is theta. Okay, so if this is vertical and this is the radius, so this is a sphere, this is big soccer ball or football. If this is vertical, then this is radius, then radius makes the radius aligns with the vertical, 0 degree. Now radius grows, 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 and when it is 90 degree, it comes to xy plane, means 90 degree it comes to the plane, then it grows till 180 degrees. So 180 degree to 0 degree radius moves. So if radius has length p and at any moment it makes phi angle with vertical p phi, so okay, then how we calculate the volume? So let's quickly, so what we are trying to show now is that the question why multivariable calculus came into the picture. Now, with the kind of scenario that we are seeing in the machine learning or artificial intelligence, where we have a class, class has set of attributes. So, class instantiations are nothing but the data sets data. If I have a data set of data, and data set belongs to a particular class, data set may belongs to n number of class, but for a particular class in the data set, if there are so many samples, means so many instances are there, and then the features inside a class are attributes. Okay, feature must be orthogonal to each other for non-collinearity. If they are not orthogonal to each other, then the information, the set of feature, the information they would carry, so separate instance of the kind of data set of the class, the information, if there are n number of features, and the information what they contain would be not very high. Okay, probably if n is 1000 and I have only 5 orthogonal components as feature, those 5 may contain more information than 10,000, 1000 features. So idea here is that feature must be orthogonal to each other. If they are not, then it should pass through some kind of mathematics, so that there should be reduction in the number of features. But whatever end we receive, whatever we filter it out, it should be orthogonal to each other. So that's why dimension reduction ability that comes into the machine learning. Whatever. If the number of orthogonal features are more than 3, then situation starts kind of, it is grim. That how we can imagine it, how we can interpolate it. In that sense, now so many things are coming. So up to 3, we have XYZ. Beyond that, we came to density. But now, if we see the polar coordinate or cylindrical coordinate, so polar coordinate is in a surface. So if it is a radius, then one component, and then angle is another component. Then for third degree we have z. Now for fourth degree we have density. Okay, so this is polar and cylindrical coordinate. As far as spherical is concerned, if I have a sphere, then if this is the radius of the sphere, then it will move in 3D. So from vertical, if it is a 5 degree, okay, this is one thing. So radius is one thing, phi is another thing, two orthogonal. Radius is one thing, make phi angle with the vertical, that is another thing. Now, if I do radius sine phi, it will directly fall on this surface. So radius sine phi falls on this location. Now, this is the polar. There anyway we have two things, another radius and another angle on which it will rotate in the plane. Please concentrate. So, if this is the sphere, football, in that sphere, from center of the sphere, if this is the radius, then from vertical, if it makes angle phi, from vertical, it makes angle phi. If it makes angle phi, then phi is one component, one feature. Radius is another feature. Radius sine phi falls in this plane, polar plane. In polar, wherever it falls, that radius is another thing. Then it may rotate 360 degree on that plane. That theta is another. So we have so many orthogonal components. Okay, we are growing. And then the sphere density. So the idea is that if we keep thinking and move into kind of a new thing, then we can grow in the dimensionability as far as the number of dimensions. So Cartesian x, y, z. If I leave the Cartesian, we enter into polar, then cylinder, then spherical. Then there is another component called density. Okay, but so what? What kind of what we are looking for? So deliberately we are thinking of growing the orthogonal component. We are looking here, there, and whatever. Okay, so one solution is whatever we have now, Cartesian, polar, or cylindrical, or a spherical coordinate system, whatever we have, plus density. So one solution is if want to grow, then we can have in kind of hybrid mode, where we can think something mixture of Cartesian, polar, and cylindrical and spherical. Spherical is anyway it contains polar also. Okay, cylinder also contains polar also. So whatever, then density, Cartesian, polar, and cylindrical and spherical, everything we create the hybrid, then probably we can grow in the orthogonal dimension. If we are not inventing anything new, but invention never comes in one go. Okay, so a person sitting nicely and suddenly he cannot invent field effect transistor. Okay, so field effect transistor FET is not possible that someone would invent immediately. He had to start from the kind of diode or whatever, and that too, the prior diodes were different than semiconductor diode, and then slowly it came to semiconductor diode. Then from diode, semiconductor diode, it came to transistor, and then slowly, field effect transistor came. So in one go, no one can invent field effect transistor. So in one go, no one can invent better better kind of orthogonal component, the model as far as the coordinate system is concerned. So whatever we have now, we can think of creating more in it. Then slowly invention comes into the picture. This is how invention happens. Whatever the resources we have, maximum we can think of hybrid, creating the hybrid. Once hybrid has come, slowly idea comes in the mind, and then we can come with the new kind of coordinate system. But this is the kind of struggle. This is kind of the approach that people are making to have a better coordinate system. So that is the scenario. So quickly we'll see the kind of a density function, and as far as the its use. So because density function looks like it is the future, rather than going for independent component in the next kind of orthogonal component. Like if I have xy component and then fxy is z, that is dependent component. So dependent component z is dependent upon x and y through function fxy. Now, if this is the plane, then this is x and this is y, then this is fxy. This is the orthogonality. But as far as density is concerned, if this is the plane, then in the plane itself from the origin to other places, we have density. So fxy, either we consider it as vertical, or fxy, I can consider it as density of the surface. So if it is 1 plus xy, then at 0, 0 density is 1. 1 plus x into y. If it is at 10, 10, then density is 1, 0, 1. Okay, so density grows as x and y, they grow. Okay, otherwise someone can imagine it as vertical component. But best thing about the density is one more dimension we can see. Now, if I do fxy dx dy, dx dy is area, and into density if I do, then it will bring us volume. Volume in a sense that if I consider fxy as z well, but if I consider it as density, then it will bring the net weight of the plate. Okay, or so net weight of the plate. If I consider fxy as 1, fxy as 1, so dx dy is area and fxy is 1. So dx dy into anything, it will be considered as vertical. So now it constitutes a volume which has height 1. Okay, but in multiplication height 1 means nothing, right? So if fxy is density function and it has a function in xy, then it gives the variable length, variable weight, where the weight is what. But if it is 1, then it gives the, because fxy dx dy, fxy is 1, as good as it is not available there at all. So dx dy would give the area. So either it affect the density function. If it is 1, then we get the area. If it is not 1, then we get the net weight. Okay, or if it is fxy is vertical, then we get the net volume. So these are the way we think, because we have to grow now. In 3D also, if fxy z dx dy dz, so dx dy z dz is dv, that is the volume. If fxy z is 1, then we get the volume. If fxy z is not 1 in the function of xyz, then we get the net weight of the volume. So this is the analogy of density function. Either it is 1 or it is in function of xyz, what we want to calculate. So the fundamental of fxy as thinking of another orthogonal component as far as dependency is concerned, that era is going up. Okay, so now density function is coming into the picture. Now if I am thinking something in x, y and z, then we go for Cartesian. But we have something in kind of circular way, okay, or a spherical way, then we are thinking in polar, cylindrical and a spherical. So polar, if I say, if I have a circle like this, if I have a circle, this is a radius, if this is radius and I rotate the radius, it brings a circle. If brings a circle, if radius is r and angle is 2 pi, then area is, okay, if I'm sorry, if the radius is r and it rotates like this, the circumference what it is making with 2 pi angle is 2 pi r. So with 2 pi is the angle, that is 360 degree. So 2 pi, if it is 2 pi, if I 2 pi, then the full circumference is 2 pi angle into the radius. If it is theta, okay, from here to here, it is theta, then arc is theta r, r into theta, that is the arc. If theta is 2 pi, then 2 pi r is the circumference of the circle. Now, if I have a circle, if I have a circle and I want to calculate the area of the circle, then now now suppose that this is r. Okay, I really have circle. So okay, so if this is circle and now this is center and this is radius, then this radius is variable. So if I take this as radius from here to here, only this way radius, and then I take delta r. So radius 1 and then radius 2. There are two radius, one radius and second radius. One radius and second radius, two radius. The distance between R2, so R2 minus R1 is delta R. So I can say there is one radius R and then delta. Okay, now with delta R, we have a arc strip. With delta R, we have a R strip. What is the area of the R strip? When the strip has angle theta, the angle between the arc strip, what we are saying, this has angle theta. So the arc strip, it is very small, then arc length and then width multiply, I get the area. So this width is delta r and this arc is r d theta, if this is d theta. R d theta dr is the area. Now, since we found the area of the small strip through algebraic equation, that is the class, through algebraic equation. So algebraic equation in integration, please see the past video. So algebraic equation in integration, if I have, then I can integrate it. So r d theta is the arc and dr is the area of the strip. Then if I want to integrate it, then r will come from 0 to a, that is the full radius, and angle will be 0 to 2 pi. Whatever we get, so 0 to 2 pi and 0 to a r d theta dr is the surface area. Now if I have a surface area like this and this is cylinder, okay, so if I grow this become a cylinder. Okay, if I grow this, then this would become a cylinder. Okay, so if I grow this, then this would become a cylinder where the base is again a simple mere circle. So circle on and height, this becomes a cylinder. Now, if I say that I have a function called f r theta, f bracket r theta, f braces r theta, a function on r and theta. If I have a function on r and theta, then f r theta r d theta dr, it becomes a volume. If fr d theta is z component. If it is z component, then height into area becomes volume. Now we can go for density function. So fr is a matter of understanding. Either we can consider this as density function or we can consider this as a height. So fr theta can be height or it can be density function. So if it is height, fr theta r d theta dr is the volume of the cylinder. Or if I say fr theta is the density function, then it gives the weight of the horizontal circle. Okay, or fr theta is 1, then it gives the area. Okay, now if fr theta is the height, then it gives the volume or weight, whatever. So weight is like volume only. Anyway, now this is the scenario. So now, okay, so this is kind of, if I want to go in 4D, this is 3D, 4D. So in 4D, the z component will also comes into the picture. So f r theta z, f r comma theta comma z in bracket, r d theta dr dz. Okay, so r d theta dr dz is the dv, the volume. So volume into density will give the weight of the cylinder. But if f r theta z is 1, then anyway it gives the volume. So we can calculate the volume through two ways. Can you see, if f r theta r d theta dr, where f r theta is the height, then again we are calculating the volume. Or f r theta z r theta r d theta dr dz. Okay, in triple integration, if f r theta z is 1, then also we are calculating the volume. But this is through density function. But in other case, f r theta was the height. Okay, so density function and height, this confusion should be clear. So density function gives the weight, or it will give you so kind of uniform weight or the area or the volume. So cylindrical coordinate, where if we go for triple integration, then we have the surface area, that is r d theta dr multiplied by dz. Now we have density function as fr theta z. Now if I go for triple integration, we get the net weight of the cylinder. But if it is 1, then we get net volume. Okay, so that is the cylindrical coordinate system. And then spherical coordinate. So spherical coordinate system, we really have one sphere. So this is the sphere. Okay, it is very small. So this is the sphere we are talking. So okay, so this is not simple sphere. Okay, it jumps also. So this is the sphere that we are talking. So sphere, the inside this, from the center of the sphere, there is a radius. So from the vertical, it makes phi angle. it makes phi angle, then radius sine phi will fall into the horizontal plane. So radius sine phi will fall into horizontal plane where our polar coordinate system is ready. So if we are trying to calculate the volume, then if it is P, then P sine phi falls here. Okay. If it falls here, then if I multiply this by d theta, then we get the arc. Okay. How to calculate volume of a sphere? Now, in polar coordinate, we had taken a circle and then we took a arc and dr. So that strip we take. So that was in 2D. That strip was in 2D. Now, if it is a volume, then anywhere in the volume, I'll take a small kind of chunk of small chunk of the mass that is del dv, not dA, dv. It is volume. So if it is volume, so if this is center, so at radius p, say from center at radius p, where p is variable, it is not touching the end of the sphere. So if at radius p, this is radius p up to here, there is a volume. This is volume. See, this from center, if this is radius p, then this is the volume. If this is volume, then volume has three sides. So if this is P, then I consider this as delta P, the way we consider delta R there. So if this is P, then this is delta P. If this is delta P, then one side of the volume is over. That is delta P. Now other side of the volume, if this is angle phi, then P delta, or this angle is delta phi, d phi, I'm sorry, if this is the volume, small volume, if this is the small volume at location P, okay, then it has three sides of the volume. So one side is delta P, other side is the angle of the volume. If this angle is d phi, then P d phi is one side of the volume. So one side of the, there in polar coordinate it was r d theta, r d theta. Here P d phi. So P d phi is one side of the volume. D phi dp delta P is one side of the volume, and P delta phi is one side of the volume. The third side of the volume, if I say sine theta, sine phi P, it comes into this plane, and then delta theta. So P and this angle from vertical is phi. So P sine phi, P into sine phi falls on this plane. So this, now this in this plane is P sine, it won't be this much P, it will be reduced. So P sine phi is here. If I move delta theta, then this arc is P sine phi delta theta. So now for the delta V volume, we found the all three sides. One is delta P, another is P delta phi, and another is P sine phi delta theta. So P sine phi delta theta into P delta phi into delta P. So that is the volume of the small section we have taken, 3D section. Now that volume we have to now see, since it is in algebraic equation, we have to generalize for the full sphere. So now it will come to triple integration. If it comes to triple integration, then P sine phi d theta, P d phi dp. So these are the three things. The P will integrate from 0 to full A, full radius. And then phi will integrate, a limit will be 0 to full pi. From if it is 2 pi, then this is this surface, then full pi. And then the theta in this plane 0 to 2 pi. So theta will move 0 to 2 pi. Phi will move 0 to pi, and radius will move 0 to A of the sphere. Now this becomes kind of volume of the sphere. now again we have f theta p, f phi, p theta. These are the three orthogonal components we see. Now, if I have function over it and it is a density function, then we calculate the net volume. Okay, net mass. I'm sorry, net mass. I'm not interested in your net mass. I want volume. Make it 1. Then you will land up into phi p sine phi d theta p d phi dp, okay, into 1. Integrate it. So p integrate 0 to a, phi integrate 0 to pi, limit 0 to pi, and theta 0 to 2 pi. Then you will get the sphere volume. If f r phi f pi, p phi theta is 1, if it is not 1 and it is in function of p, p, phi and theta, then you calculate that is nothing but a density function, and you land up calculating the mass of the sphere. But mass is not the kg also. It can be, what is the density function? It can be population, it can be anything else. Depends upon the unit of the density. Done. Now we'll take an example quickly and we'll see, like suppose that I have to calculate volume of this sphere. Volume of this sphere. Then volume of this sphere means F. I have to calculate the volume, not the mass of this sphere. Okay. So volume, if I say, then I have equation in spherical coordinate. If I see, then F P phi theta is a function over P phi theta, where P is radius any place and phi is from vertical, what is the angle, and theta P sine this P phi, P sine phi that falls in this plane, and that is the theta. So F F P, P is the radius, Fp phi theta function over theta, phi and P, and then P sine phi d theta P d phi dp. This I have to integrate. So if I am calculating the volume, then Mr. F P phi theta, the function over it becomes 1. The density function becomes 1. Now I have to calculate the integration. So P sine phi d theta P d phi dp becomes P square. P square sine phi d phi dp d theta. Okay. Now P I have to say 0 to a, and then phi 0 to pi, and theta 0 to 2 pi. So p square becomes aq by 3. Okay, and then another one is sine phi. So sine phi, integration of sine phi will become minus cos phi. Then from 0 to pi, both are 1. So minus cos phi will become 2. So 2a square by 3 is the volume. Now third one, theta will become 0 to 2 pi means 2 pi. So 4 pi aq by 3 is the volume of a sphere. 4 pi aq. So it is 2 pi into 2 into aq by 3 component wise, and that is the volume of the sphere. Okay, now let's calculate volume of the sphere through polar coordinate. This much you will not get any. So let's calculate through polar way. Now we calculated through spherical way. We'll calculate through polar way. Polar way means I have only the surface. That's it. So polar, if I am calculating the kind of the volume. So if I want to calculate the volume, let's go through density way. So polar plus height, that is cylinder kind of. So now if it is cylinder kind of thing, then the density function, if we want to calculate the volume, density function will become 1. Now we are calculating r d theta dr dz. Okay, so if I am calculating the sphere through polar coordinate, I have to calculate the volume of a cylinder, not the sphere. But we will do some kind of tweaking or intelligence. So r d theta dr d d z. Now density function is 1, that is f r theta z is 1. Now the first integration will make for the r. Now just see it. If this is a surface, now this is a sphere. If I cut down at the origin, okay, inside it there is a origin. If I cut down origin and I have a plane, so in that plane I have r and theta. So the area of the plane is r d theta dr. Okay. Now, but this is area of the plane at the origin. If I go up, this is origin. If I go up, then area will become smaller. If I go up, because this is a sphere, this is not cylinder. If I go up, then at the top there is no area. So at the top we see the top of the sphere. So from the top of the sphere, if I come down, the radius, the cross section radius, because polar coordinate is cross section radius. So at the top, the cross section radius is 0. Keep coming. At the origin, the cross section radius is maximum. Then if you keep going down, at the bottom of the sphere, okay, at the bottom of the sphere again, the cross section radius is 0. Okay, this proves that radius is dependent upon the z factor. Okay, so at any z, what is the relationship between radius and z? Okay, so if this is the cross section, this is cross section at the origin, this is cross section at the origin. At height z, there is another small cross section. Now in this cross section, this is the radius. Okay, if this is the radius, then this is the boundary of the sphere. This is the sphere, and this is the cross section at height z. This is the cross section at the center, that is the biggest cross section. At height z, there is another cross section. So if this is the radius r, then this is the z, then this is the a, that is the radius of the sphere. Then r square plus z square equal to a square. That is the relationship between r and z. Because if z is growing, the cross section radius is decreasing. In Cartesian coordinate, we say any point in the sphere is x square plus y square plus z square equal to a square. That is the radius of the sphere. Forget the Cartesian now. Okay, so the relationship between Cartesian and polar, or relationship between Cartesian and spherical, is that the x is r cos theta, y is r, x is r cos theta, y is r sin theta, whereas x square plus y square equal to r square. In a spherical, x square plus y square plus z square is a square. Okay, that is the radius. Otherwise, if this is the radius, then a sin phi is this plane. Then if this is the radius a and this is phi angle, a sin phi falls in this plane. Okay, somewhere in this plane. Then cos a sin phi cos theta is the x, and a sin phi sin theta is the y. This is x and y. A sin phi cos theta is a sin phi sin theta is y. Okay, this is in spherical. Anyway, now we are calculating the volume through polar coordinate. Now in polar coordinate, if this is the surface at center, the biggest cross section, z above small cross section. So in small cross section, if r is the radius of the cross section circle and the z is the height, then radius square plus z square is the actual radius of the sphere. So r square plus z square equal to a square. So the radius equal to a square minus z square. Can we see that r square plus z square equal to a square? If z is growing, a square is constant, so r is decreasing. So at the center, when z equal to a, r is 0. So if this is a sphere, then at the top, not at the center. So at the top, if we go from the center, if I make the cross section, if we go up and reach that apex top, there the section cross section radius is 0. R square plus Z square equal to A square. A is the radius of the sphere. If Z equal to A, then R is 0. If Z equal to 0, then R is A. That is the biggest cross section. Now we are integrating R d theta dr dz. So R is now, if R becomes, if I integrate it, R becomes R square by 2. Now R square by 2, now the integration of the R is, okay, from 0 to, because R is in function of Z, because R is varying, R is not constant. So from 0 to R is A square minus Z square square root. R square plus Z square equal to A square. So R is A square minus Z square square root. If that is the case, then 0 to square root A square minus Z square. So R square by 2 is the integration. It will come as A square minus Z square by 2. Now Z we are integrating, that will be 0 to A. Full we are integrating. That is the hemisphere we are getting. 0 to A is hemisphere. So R A square minus Z square by 2. If I integrate with dz, then A square Z minus Z cube by 3 by 2. Okay. Now if I substitute 0 and A, then it will become A cube minus A cube by 3 whole by 2. So that is the case. Now theta will integrate 0 to 2 pi. So AQ minus AQ by 3 by 2 into 2 pi. So 2 will cut down and pi will remain. So pi into, in bracket, AQ minus AQ by 3. That will come as 2AQ by 3. So pi 2 pi AQ by 3 is the volume of hemisphere if I take Z from 0 to Z. Multiply by 2, then 4 by 3 pi AQ, or the Z integration I had taken from 0 to A, I should take minus A to plus A. Then 4 by 3 pi AQ is the volume through cylindrical coordinate or polar coordinate system. Now there is another question. Suppose that there is a water tank. There is a water tank. These are famous questions. There is a water tank that is hemisphere. Water tank is hemisphere where base is cut. If I cut down the sphere at the center, that is the base, and then it is a dome, circular spherical dome. Okay, so now the cross section radius is A, and from center top radius is A, the way hemisphere happens. What is the net volume of water at any height h or any height z? If there is a, from the bottom, if there is a height z up to there water is filled, what is the volume of the water? Now what we have done is r d theta dr dz. Integration is r is from 0 to a square minus z square square root, where z has integration 0 to a full radius. Okay. Now z is going from 0 to top. Now it will go from 0 to z1 or 0 to h1. That is the integral. No change. So r square, sorry, so r square by 2, same thing, a square minus z square by 2. Now if I integrate with z, then a cube z, then a square z minus z cube by 3 by 2. Now multiply by 2 pi at the end, then it will become pi into a pi into z cube minus z cube, I'm sorry, pi braces a square z minus z cube by 3. Okay, so pi into a square z minus z cube by 3. If I take z out, then pi into z braces a square minus z square by 3. So at any height z, that is the volume of the water. So this is something that, so what is the concept here? Concept is that you have to check the limit, whatever limit you have, because inside it will be f r theta z, r d f r theta z function over r theta z, f r d theta dr dz1. If you if r theta z, a function of r theta z is 1, you are calculating the volume. Otherwise, you are calculating the mass. Okay, but main thing is limit. What limit you take? Be careful that one is dependent upon other. If one is dependent upon other, then independent integration will happen first. Like r is dependent upon z, then r integration will happen as the inner. Then outer is z, and then so the outermost will have the integration limit as constant. So that is not, that is the most independent, that is the most independent. So dependent, independent, independent, the most independent will have the limit as a constant. Okay, another example can be that if this is cylinder, if this is cylinder and this is circle, if this is cylinder, this is circle, I cut down the cylinder like I have a cake. So cake is in form of cylinder one. There is a base circle, and then okay, and then circle. That is the cake. If I cut the cake as a wedge from the center, if I cut at an angle that is theta, and then I cut it, so cake height is h, angle is theta, and radius is r, then what is the volume of the cake? Or what is the weight of the cake if it is density? So that again we will calculate r d theta. If I have to calculate the volume, r d theta dr dz, where r is from 0 to a, that is the full radius. Then z, whatever the height of the wedge we have taken, so 0 to that much. And theta, if I cut the cake into the cake, then what is the angle? 0 to that much. Or if I am taking angle from 0, then that angle to that angle. Okay, so easy, right? Means now the intelligence, can we see that why we are moving from Cartesian to angular one, and then net dependent component over independent to density one? We are want to somehow grow into number of dimension somehow. And now there are hope that we are at 4 dimension now, we can grow it. So it is something like we are trying to control the machine learning. Okay, so mathematics is nothing but you try to control whatever is happening through your formula. That is mathematics. If I am seeing that if I am heating something and gas is coming out, and gas is changing the volume, and gas has a temperature, volume, temperature, so many things, then it has so many dimensions. Then the way it is changing the mass or changing its size, and there it is losing the heat, so many factors are coming. What I would do is I try to put them into the equation. Once equation is ready, then I can estimate the future, because gas is changing in that fashion, and heat it is liberating, and then it is changing color. If every attribute, if I place in an equation, then I can say after half an hour what is going to happen. Okay, so this is artificial intelligence. But main problem that is coming is we are not able to put into mathematical equation, because dimension, the number of attributes, what we see anything happening is too high. Sometimes 1,000, 10,000 attributes. So those many dimensions are not possible. Changing it to orthogonal component is challenging. Can you see now? Cartesian to polar to cylindrical to spherical. All these hops are happening for coming to kind of curving the AI, artificial intelligence. Anyway, okay, so we are in a step, we are in a kind of, we are in a way to go beyond the 3D. So we are succeeding somewhere. We will succeed.